If you stand on a beach and look out over the ocean, the horizon forms a perfectly straight line. Trusting that intuition is often dismissed as a misunderstanding of scale, but the direct geometric observation of a flat horizon is a valid starting point for inquiry. Overhead, the sun and stars trace rigid, cyclical paths every single day. From this perspective, the sky appears as a dome, a firmament bounding the world in. Lacking access to advanced manifold theory, a localized observer concludes that these two observations, a flat horizon and a repeating sky, require the Earth to be a planar, bounded surface. The problem lies with the topological framework. Our understanding of geometry changes how we interpret what we see, a challenge that persists even when we look at the largest structures in the universe. At the cosmic scale, our standard model of cosmology, lambda CDM, is formally broken. The mass and gravity we observe in deep space fails to align with the equations used to describe them. Keeping the math balanced requires inserting invisible, ad hoc terms. We call these dark matter and dark energy, though neither has ever been directly detected in a laboratory. The breaking point is the Hubble tension. Measurements of the early universe and the local universe produce expansion rates that are statistically incompatible, suggesting the core of our model is missing a vital component. Whether looking at the horizon or through a telescope, the core issue remains the same, attempting to force physical reality into an incorrect geometric shape. Resolving these contradictions requires a restructuring of the universe's shape. The Integrated Toroidal-Syntropic Model, or ITSM, proposes that the cosmos is a 3-torus manifold. A 3-torus is globally periodic, meaning it loops back on itself, while remaining intrinsically mathematically flat. Think of a coordinate grid rolled into a cylinder, then curved until you connect the ends into a donut shape. In this manifold, local spatial curvature is genuinely zero. To an observer at this scale, the horizon appears perfectly straight, because the local geometry is Euclidean. Global periodicity causes light to wrap around these boundaries. This creates a topological hall of mirrors, where celestial objects trace cyclical paths across a sky that appears bounded and repeating. A toroidal universe accounts for both a flat horizon and repeating celestial paths within a single consistent geometry. This toroidal manifold contains an active superfluid plenum. As galaxies spin through this medium, they displace the fluid. This generates a sustained acoustic wake that trails behind the baryonic mass. Standard cosmology measures this hydrodynamic drag as dark matter. In the ITSM, the gravity of a halo is the physical resistance of the vacuum plenum itself. This geometry also dictates how we measure expansion. Depending on the observer's viewing angle relative to the torus, measurements will vary by exactly 8.3%. This chart shows how both the Planck and SHOES values fit into the same geometric curve. Relying on fixed topology and fluid dynamics replaces the search for invisible particles with precise geometric laws. Scientific models succeed by generating falsifiable predictions that challenge the status quo. The ITSM describes an open thermodynamic system. This structure actively accelerates the assembly of mass during the earliest epochs of the universe. Deep field surveys from the James Webb Space Telescope are currently finding anomalously massive galaxy clusters. Structures like XLSSC12 are 32% denser than standard models allow, appearing much earlier in the timeline than predicted. These mature early galaxies are the expected result of a toroidal universe and its unique causal horizons. This brings the perspective back to the human scale, standing on a beach and looking out over the water. Our universe operates as a harmonious, self-stabilizing system. The true cosmic architecture is a globally periodic toroidal manifold. This wireframe maps the phase-space currents that guide the flow of energy across the entire cosmos. Looking at a perfectly flat horizon is a direct encounter with the geometry of the universe. You are witnessing a localized, low-dimensional shadow of the same laws that govern the stars.